All right, today we're going to look at 2.2, so a numerical and a graphical approach to limits. Graphs below represent the positions of moving particles as functions of time. Determine whether each particle is speeding up or slowing down. Okay, and so we're going to take a look at the rates of change in terms of the tangent line. So the first one has tangent lines sketched for you, and you can see that as we move from left to right across the graph in terms of time intervals, our tangent lines are getting less and less steep. So if a slope is less steep, then therefore the rate is slowing down. So if we did the same idea over here, and we take a look at a rate of change, a tangent line there, and there, and there, we can see that we are getting steeper, and therefore we are speeding up. Okay. So this was just a graphic, an example from your homework where we were matching graphs in terms of speeding up, slowing down, etc. So if we were to take a look at the graph that shows that we are speeding up consistently, we would match that down here with graph D. Something that is speeding up and then slowing down. If I look at B, I'm getting steeper, but then I'm getting less steep. Something that's always slowing down, that would be A. Something that's slowing down, it's getting flatter, but then it's getting steeper again, would be graph C. Okay, so key question with limits. How do the values of a function f of x behave when x approaches a number c, whether or not f of c is defined? So that's super important here, right? So the graph could have a hole there. It could be discontinuous in some fashion, but we're taking a look to see how does the function behave. So let's start by looking at a table of values. What is the limit of the following function as x approaches 0? So the function is sine of x over x in radians. So we know that we're undefined here because x equaling 0 can't be in the denominator. It's a domain restriction here, just as a simple example. But we can still evaluate and look at behavior of this graph or this table of values near 0. So the notation that you're going to get familiar with is right here in the box. Limit as x approaches 0 of f of x is how you would read that. So the table of values is showing values as x approaches 0 on the positive side or from the right. Okay. So if we start with 1 and we get closer and closer to 0 fractionally or decimally, we can see that the y values, the output of this function, go from 0.84 and then they approach 0.99 repeated. And if we do the same thing on the left-hand side, so x approaching 0 with a negative sign means from the left. Same idea, we start at -1 and we work closer towards 0, and those y values, the sine x over x values, also get to 0.99 repeated. So the conclusion is that the graph, the function, the behavior, the y's, approach 1. So the graph or the function is not defined at the ordered pair 0, 1, but the behavior or the limit does exist and it approaches 1. So we could do the same exact problem graphically, and most people would argue that if I can look at a graph, it is a lot easier to give the answer to this question because I can visually see it. But it is really important that we analyze from both sides. So same question, limit as x approaches 0 of f of x, and f of x is defined as sine x over x, so at 0. So in terms of x, I always like to think of it as like that vertical asymptote. Okay? When x is 0, what is the graph doing? So on the left-hand side, my y values are approaching 1. And on the right-hand side of 0, my y values are also approaching 1. So because the behavior of the graph is coming together at the ordered pair 0, 1, even though there is a hole, f of 0 does not equal 1, but the limit at 0 does equal 1. So behavior of graph. So this is what I've been talking about, but here's some notation. So when determining a limit, we need to approach the x value from both sides, left and right. We call these limits one-sided limits, and one-sided limits are notated as follows. So x approaches c with that negative sign there, from the left is how you would read it. X approaches c with the positive sign would be from the right. So in order for a limit to exist, the left and right hand limits have to be equal. So if the limit as x approaches c from the right equals the limit as x approaches c from the left, which is equal to some value L, then the overall limit as x approaches c of f of x is also equal to L. Okay, taking a look at this both graphically and numerically, limit as x approaches 9 of the function of the equation x minus 9 over square root of x minus 3. Again, we are picking a number, a value 9, where the function, the graph, is not defined there. I could pick any other number and get an answer, but in this case I'm picking 9 and I'm undefined. So I have a hole in my graph. I can graphically look on the left side and I look at the y values as I move closer to the x value of 9, and the y values as I move closer on the right as well. And graphically speaking, the y value's up there at 6. Numerically speaking, numbers to the left of 9, 8.9, 8.99, etc., my outputs get close to 6. If I look at numbers just bigger than 9, 9.1, 9.0001, the numbers approach 6. So therefore, the limit as x approaches 9, x minus 9 over root x minus 3 is equal to 6. Okay, here's an example of a continuous function. If we look at x squared, there's no domain restrictions here. X can take on all negatives, all positives, and 0. So if I'm evaluating the limit as x approaches 4, I don't have a hole. I have a normal function value filled in circle. So I still go to my x value of 4, the left side, the right side. They are both approaching 16. As would be true if I took 4 and plugged it in, I would also get 16. Limit is equal to 16. I can see my table of values. Same pattern holds true. So we'll look at limits where the function exists at that moment. We'll look at limits where the function does not exist at that moment. Another example where the limit does not exist. We want to find the limit at 0, but 0 cannot go into the denominator. So we think about h approaching 0 as sort of a vertical line. We can look on the left side of that line, on the right side of that line. Where do the numbers, where do the y values, the function values converge to, approach? How do they behave? So if I were to trace this graph, I would want to trace straight through the number 1, the y value of 1. So even though the function is not defined at x equals 0, the limit as x approaches 0 still exists and it is equal to 1. That's a really important component of calculus. The function does not have to exist for a limit to be defined. Here's a graph. Here's a function where we can't find the limit at 0. Okay, this is one of those examples. We would refer to this, because I can't find a pattern, it oscillates, it bounces back and forth. There's no way I could predict at 0 what is going on. It could be anywhere between -1 and 1 as this graph appears. So this does not exist. DNE would be your abbreviation. If I looked at the table of values, you could plug this into your graphing calculator and manipulate your table of values. You would have the same thing happening where the y values bounce back and forth. They don't follow any, I won't say they won't follow a pattern, because they will follow a pattern when they're bouncing, but they won't converge to a certain number. Okay. Okay, so these examples, we're asking to look for one-sided limits. So the problem is presented as f of x is equal to x over the absolute value of x as x approaches 0. So we're first going to look at it from the left, then we'll look at it from the right. So at 0, again, that vertical line. So if I'm looking at it from the left, I'm over here, and I'm looking to see where are my y values going. What's the pattern or the behavior of the graph? Those y values are approaching -1. And if I look at it from the right, just to the right of my vertical line, approaching or working back towards 0, my y values are up there at +1. Because these two values are not the same, because the one-sided limits are not equal, therefore, limit overall I'm sorry. Let me backtrack. Does not exist. Okay. So your one-sided limits exist. There's nothing wrong with them, but they're not the same. Therefore, the overall limit does not exist. Okay. So let's fill in this 6-question example. We're looking at the graph above for all of them. So the limit of f of x as x approaches 2 from the left. So get your vertical line at 2. And if you want to pause the video here, try this on your own, and then listen to me fill it in. That would be a great idea. So limit as x approaches 2 on the left. I look at my graph over there. The function is going up to 3. If I take a look at x approaching 2 from the right, the y values are going to 1. Therefore, they're not the same. The limit does not exist. If I go through the same thing with 4, so 4 on the left, it's approaching, we'll estimate that to be 2. And if I go on the right, also 2. Because those are both the same, the overall limit is 2. Okay, we can also have infinite limits, right? So if the limit as x approaches c, some value, some true vertical asymptote of f of x equals infinity, this happens if the function increases without bound as x approaches c. Or it could be negative infinity, so it decreases without bound. So this is an example where the left-sided limit, as x approaches 2, the left-sided limit is negative infinity, because this is going down forever, where the right-sided limit is going up forever, so that's positive infinity. So the limit at 2 does not exist because the behavior is not the same on the left and on the right, but the one-sided limits exist. Here's an example of an infinite behaviored graph where the limit will exist because the left and the right are both approaching positive infinity. As x approaches 0. Right? They're both going up forever. Okay, so here I would like you to pause the video, sketch a graph, a possible graph right? Everybody's answers could be slightly different, which satisfies those above conditions. So the limit is f of x as x approaches 1 is equal to infinity. So that's not a one-sided limit. Therefore, I definitely have same behavior. I have a vertical asymptote. My graph is definitely going up there. I don't know what else is happening, so all I'm going to do is put positive arrows to the left and to the right of 1. 3 on the left-hand side goes to 0. 3 on the right-hand side goes to negative infinity. So at 3, I have another vertical asymptote. So to satisfy both of these, 3 on the left goes to 0. I have to have a hole there. 3 on the right is going to negative infinity. So now that I have no more information, I just need to continue my graph so it looks complete. And that's the part that people could do anything they want with. So I just chose to have them going off on the left-hand side, going off towards negative infinity, on the right-hand side, going off towards positive infinity. You could end it with ending points, but we don't have any other information. Okay, so final slide again. This homework may be accurate, but it might not be, so just follow along in the modules. Some closure questions for you to think about, and you can follow these up in our Zoom lessons. What is a limit? How can we determine the limit of a function at a particular x value using a graph? How can we determine a limit of a function at a particular x value using a table of values? And when does the limit of a function not exist? So if any of those questions are unanswered for you, I would highly suggest going back through the video, pausing, listening, and then asking questions during our Zoom. Okay, take care. Bye for now.